So in this part lecture, we will discuss the second order condition of the convexity of a function. That is, any function that satisfies the second order condition has to be a convex function. So let's assume that function f is twice differentiable. Assume there's a function f, which is a mapping from an n-dimensional real vector to a scalar, and it is twice differentiable. So if a function is twice differentiable, which means that the second derivative or the Hessian exists, that is, the domain of f is a convex set. So this is an underlying assumption. The domain of the function has to be a convex set. And the Hessian or the second derivative exists at each point in the domain of the function, which means that the domain is an open set. Only then the second derivative will exist at each point in the domain of the function. So if this condition holds, then f is convex. If the second derivative of the function is a positive semi-definite matrix, then f is a convex function. In case of 1D functions, that is, if f is a mapping from real space from scalar to a scalar, then this condition translates to the double derivative of x being non-negative. So if this condition is satisfied, that means that the function is convex. Given that the domain of the function is a convex set, subject to condition that the domain of f is convex. So any twice differentiable function that satisfies these properties is convex. And for strict convex functions, if the Hessian is a positive definite matrix, then the function is strictly convex. But the converse is not true. For example, all strict convex functions don't need to satisfy this condition. For example, x to the power 4 is strictly convex, but the f double dash x at x equal to 0 is 0. So the converse is not true. All the strict convex functions, twice differentiable, don't have to satisfy this condition, but this condition is again a necessary and sufficient condition for twice differentiable functions for them to be convex. Now, what are positive semi-definite and positive definite matrices? So let's assume there is a matrix P, an n by n matrix. So this matrix is positive semi-definite if and only if for all v in the n-dimensional real space, v transpose times p times v is greater than or equal to 0. In other words, all the eigenvalues of p are greater than or equal to 0. Likewise, for a positive definite matrix, a matrix P, which is an n by n matrix, is positive definite if and only if for all v transpose times p times v is greater than 0. In other words, all the eigenvalues of p are greater than 0. So that's it for the convexity. This is all what we wanted to discuss in the convexity section. And now you can relate all the information that we have provided you so far to sort of realize why we set the gradient of the loss function in case of least squares and in the case of L2 norm regularized least square, as well as in case of logistic regression to 0, to obtain the minimizer or the maximizer of the log function of the likelihood. So just a small sort of like note about the concave functions. So if a function f is convex with domain of f is convex, then the negative of the function f would be a concave function. And for convex function, the point at which the gradient is 0 implies the global minimizer, and for concave function with domain being convex, the gradient at which the point at which the gradient is 0 is a global maximizer. And that's why in the case of least squares, our loss function was y minus phi times w, which is a convex function. We set the gradient of the loss function to be equal to 0 to compute the optimal w as phi transpose phi inverse times phi transpose times y, right? Because we assume that because this loss function is a convex function. And likewise in the L2 norm regularized least square, again we set the gradient to 0 to obtain the global minimizer loss function. And in case of logistic regression, we maximized the objective function. We maximize the log of the likelihood, because it turns out that the log of the likelihood is a convex function, and you can prove it very easily by taking the objective of the loss function of the logistic regression. So if you take the log of the objective function of if you take the double derivative of the objective function of the logistic regression, it will turn out that second derivative is negative, which means it's a concave function. And for concave function, the global minimizer is a point at which the gradient is 0. That's why we set the gradient to 0 to obtain the optimum. And we moved so basically it turns out that for the logistic function there was no closed form solution, but still we were able to find the global maximizer by moving the direction of the gradient, because in case of convex function, if you move in the direction of the gradient, that will maximize the concave function, and for convex function, if you move in the direction of the negative of the gradient, that will minimize the convex function. And that's why for the logistic regression, the update equation was, since we were maximizing the objective function, we were moving the direction of the gradient, and for least square regression, we are moving the direction of the negative of the gradient, because we were minimizing a convex function. So that's it about the convexity. Also to realize why this norm is convex, proving that the objective function of the logistic regression is a concave function is very easy. You just take the second differential of the log of the logistic function of the logistic regression, and you'll find that it is negative, and that's why it's a concave function, and that's why the maximizer is a global maximizer. We will just discuss a brief we will just give you a brief overview about the operations that can preserve convexity, right?